introduce Petya Maneva for today's seminar. She is a speaker for today's seminar, and she is a transportation, she works as a JS specialist in Maricopa Association of Governments, MAG. She closely works with the Dr. Pendela research group. I think, yeah. They closely works with her. And today she's going to talk about use of GIS in transportation engineering. Most of the people think, how can we use the GIS in transportation engineering? Recently only we actually introduced, not recently, maybe 10 or 15 years back, they actually started mapping the data of transportation data in GIS and showing the interactive way of how actually trips go from one place to another place, which actually useful for the policymakers to take the decisions. I hope this seminar will be useful for you guys. Thank you.
Thank you for coming to my presentation. I'll try to speak louder, and also if you have questions, feel free to interrupt me on the spot. You can ask questions in the end, but it's okay if just stop me whenever you have a question. And so some of the topics I am going to try to cover today: data needs of travel demand models, how to structure transportation network datasets, how to do travel data collection and post travel-related data on web portals, and also I'll talk a little bit about travel time mapping. So, how many of you are familiar with first-step travel demand models, activity-based models? Do I need to explain a bit more on that? Okay, so in travel demand modeling, what we do is we have data sets with primarily employment and population data, also digital representations of transportation network, and we run pretty complex, sophisticated software programs that try to determine how many trips go on each and every segment of the network. What we do is the whole area for which we model, like in our case we model the whole of Maricopa and Pinal counties, so we divide the area into small zones. We have roughly about 2,000 zones, and so we estimate how many trips go between each two pair of zones, and the end result of this is that we not just determine the trips between every two zones for a given time period, but we also assign them to portions of the network. So this is a traditional four-step model where we have pretty much, we do this process fairly straightforward way. Now, the software packages that are being used, the most popular ones for first-step model, Transcat, EMI, and Cube. Our agency is using Transcat, so it's a desktop application, and so a full run for the area takes something like 8 hours, 10 hours, 13 hours. Now, we're working to implement activity-based model where each person, so each household is explicitly modeled and each individual trip is modeled. So that's a newer generation, more powerful models, and they require much longer runtime, and they require that computers work in parallel, and sometimes they require cloud computing. So how do we provide data for an activity-based model? So we use a lot of raw data sets from survey, purchased from vendors, compiled in-house, and from all these data sets we pretty much distill them into data collected at zonal level. So we have small polygons, and for every polygon we know how many jobs are there, how many people work there. And so we have socio-economic data for every small zone for which we do analysis. And the second big part of the data that feeds into a child demand model are the transportation networks. So we have a very precise digital representation of the intersections, segments of the road, and also to model transit we have to have the location of routes, and for each route we track the individual stops on the routes. So all the data I'm talking about has to be available for the year for every horizon year for which we want to model. So we have to have current data for the networks and the employment and the population, and we also need to have for future years the same data set. So if we want to make a projection for 2030, then we have to have a network that includes all the projected freeways and projected future roads in there. And we have to have a projection for the employment and population. Now you can see here the zones, so the big squares, these are analysis zone for the first step model, which is a bit older way of doing modeling that's being phased out. For the activity-based models, which are newer generation and more powerful, then we have these little blue polygons. They're called microanalysis zones. So activity-based model requires much higher resolution of all the data set. Another difference between the two models is activity-based model helps planners answer policy questions. Like, if we want to figure out would people buy more green vehicles if they can travel alone on HOV lanes, a question like that cannot be answered with the first step model. But in an activity-based model, you have to change the software, add an algorithm that's going to take into account, allow users to choose between HOV, lane, driving single on an eco-friendly vehicle versus going general purpose lane. And so to answer policy question, you have to change the algorithm. You need to collect extra data. Like, for instance, such a scenario would require that we survey people and ask them the question, okay, would you buy a hybrid if you can drive alone on a HOV lane? So this is, I want to real brief show you how the data set look like, but I'm trying to remotely connect to my computer and open the table, an actual Transcat table. So I hope I didn't lose the connection. I have, okay, it's here, but I don't see the tab that allows me to open files. Okay, so as I said here, I have the transportation network loaded. That's used for modeling. And so if I open the highway portion of the network data set, so you probably know, so it's a polyline data set, so each row represents a segment on the network. It has a geographic component, so it's a spatial footprint of a segment of the road. And it has all the description that are, all the attributes that are relevant to modeling, like the number of lanes, if the segment is one-way or two-way. It has the area type through which it goes, and what type of modes are allowed on it. So all attributes are loaded here. a route data set. It be a similar concept, so each route is gonna, each row on the routes table represent a footprint of the whole route, and then all attributes relevant to the route, like headway, vehicle type, it would be layover, the speed that's allowed. All characteristic data serves as input for us to be able to estimate what traffic is going to go on this route are going to be here. And so I guess it will be a similar situation if I open the stops table or if I open the nodes table. So maybe show you how the stops table look like. So it tells you, so here one row from this table is a stop. So it's a point. It's a point that's tied to a node on the network. So it has the route ID, it has the milepost, and other attributes that pertain to modeling. In the green polygons, these are the analysis zones. So for each of those polygons, here in the polygon table, one row will be one polygon, so it has information about the population and employments, like how types of households and type of population. A bigger level of geography are the districts, and what we do is to get a high-level view about the trends. We usually break the modeling area into districts, and those districts are used for various purposes, usually to estimate transit. So we want to determine what would be flow of people from northeast to northwest. So for a more high-level estimate, districts are created. Now, a lot of GIS work includes delineating the districts and delineating the transit analysis zone. So if you are to do this type of work, you need to figure out, well, how do I decide, how I make the decision to draw the boundaries? Because the boundaries determine, have a big impact on the output. So if they're not done well, you can skew the result, like cause the model to underperform, like underestimate future traffic, or overperform, like given too optimistic estimates of how good of an investment would be if we, say, build a light rail. For instance, we had to use those districts to figure out if there is a light rail between Tucson and Tempe, how much ridership it's going to cost. So then, if districts are not designed properly, you're going to make a wrong assessment. Now, so I want to show I try to remote to my machine. I'm switching between my machine at work where I have.
So when you're back in Congo, scroll down over here. You can see the shoe.
Okay, so it's a bit of a sidestep from transportation, but I want to explain how drawing boundaries affects outcomes. So these are congressional districts. And remember that that's the district where ASU fall. And it was a pretty competitive, and it took a while to determine the winner. Now the map, the background map is ethnic predominance, green being heavily Hispanic areas, and beige and brown being heavily Caucasian areas, and these are Native Americans in blue. These are Asian predominant areas, that's where Intel is. So I am a GIS analyst who has to design the districts. So what would happen if I decide to, this is a Republican-leaning district and this is a Democratic-leaning district. So I could go and grab these Hispanic people and move them here, and then come and bring more white people in District 9. If I were to do this, it would be very hard or maybe impossible for the current representative to be elected. Now you're going to ask me, what's the connection? Ethnicity is a good predictor for how people vote. Like Hispanic vote to 60–70% Democratic, and Asian people vote 70% Democratic on average. And so I'm not sure, I guess we don't have enough evidence that ethnicity is a predictor for child behavior, but age is a good predictor for both child behavior and voting, and so is income range. Like high-income people have a very different travel pattern than low-income people. High-income people here don't care at all about transit, while low-income people would like to have access to transit. Also, students would like to have access to transit. As far as age is concerned, also retired people have different child behavior than people who work. And so I am gonna show income versus remove the Congress. And so the orange are the zones that we use to analyze transportation. So dark green are high income areas and yellow are low income areas. So ideally, what we want to do if we design zones, we want to have people with similar child behavior be in the same zone. So ideally, you want to have high-income people in one analysis zone and low-income people with another analysis zone. So it's a rare situation where there'll be proximity between expensive and affordable neighborhoods. But if there is this situation, you don't want to have an analysis zone where half people say would be high income and the other half low income, because they have different behavior and that blurs the result of the modeling. Also, as far as age is concerned, like here for ASU, it would be wrong to have a zone where half people are students and the other half people are working. It's better to draw the line so that the whole zone has only students or only working people, because the schedules are different and the preference for transit would be different. So another example I want to give here is with the age in zones. Then again, ideally you want, if you have to model zones and there's a retirement community, you don't want to have a zone where half people are retired and the other people are working, because that's going to blur the results, skew it one way or the other. So of course, that's a very quick summary, but the bottom line is, if you model child behavior, you want to know what characteristics are good prediction, make a good prediction for child behavior. You have to have that data, know it well, and make sure within one zone you have people with similar child behavior, and put people in different child behavior in different zones.
But does that apply to the definition of districts? So when you...
Whether you're looking at microanalysis zones, TZs, or bigger district is the same thing.
So you're looking for homogeneity?
Yes. So